So this is the agenda for today's for this training session. So we are on the webinar 1 today, and we will be together for a few weeks now, up to the 11th of May. So we will have 4 statistics session where we will look at the fundamentals of statistics and up to what we can do with the energy balances and what indicators we can derive from the balances. Then we will have 4 modeling sessions by IEA modelers, followed by 2 more modeling sessions by our partners from Imperial College and Polymie. We will have another session on the Sustainable Development Goals, and then we will end with a wrap-up quiz and closing remarks on the Tuesday, 11th of May. Before we start with the technical part, let us quickly look at some of the housekeeping rules to make sure that the session today and the forthcoming sessions are the most effective. So as you see, the entire event will take place in virtual mode using Zoom, and if you need any important and urgent clarification during the session, please use the raise your hand button, and we will pause the presentation and answer your question. Otherwise, you can always use the question and answer button to ask any question during the whole session. And if we don't have time to answer your questions, we will get back to you. Otherwise, you can also reach to us on our emails. So you can reach to me, to Arnaud, and you can also send emails to the Africa program email. So this first slide is to show how the data and modeling work of the IEA has permitted to estimate the impact of COVID-19 crisis on different energy and climate indicators. A first striking discovery is that energy investments decreased in 2020 by more than 18%, or almost plunging by $350 billion. And this is mostly due to oil and gas investment dropping dramatically in the upstream, midstream, and downstream. Another discovery is that energy demand decreased by more than 5%, which was led from a drop in fossil fuel use. This is especially for oil products that witness a sharp decrease in its demand for transportation, being strongly affected by lockdown and restrictions in international traveling. This also caused a historical decrease in CO2 emissions in 2020, which is good news. But in order to achieve long-term sustainable goals, the opportunity of the crisis should be used to design recovery plans with a strong decarbonization focus. Unfortunately, the recent IEA analysis is showing that in 2021, CO2 emissions will probably rise to historic records. Another good news is that nuclear emerged as the only area that is able to contrast the trend. So real-time data collection and modeling experience really allow us to see to estimate energy trends. The pandemic has also had an impact on progress towards the Sustainable Development Goal 7 of reaching universal access to energy. Sub-Saharan Africa is now home to 3/4 of the global population without access to electricity. The number of people without access to electricity has been decreasing since 2013, and this is thanks to the progress made in several countries such as Kenya, Senegal, Rwanda, and Ghana. Still, this progress is being reversed as population without access to electricity is set to increase again in 2020. And this is due to several reasons. First, the pandemic has forced governments to shift their immediate priorities to purely emergency measures, and this results in a lack of financing available for expanding and improving electricity infrastructures. Then private companies deploying decentralized energy solutions such as solar home systems and mini-grids, they are facing operational and financial challenges. In addition, the pandemic and its consequences are also affecting populations that are already connected, and this prevents them from paying for modern energy services. So by the end of 2020, up to 30 million people who had electricity access in sub-Saharan Africa will no longer be able to have to afford basic electricity services. As a result, in 2020, close to 600 million people live without access to electricity in sub-Saharan Africa, with 5 countries being home to half of them. One of the factors limiting progress is access to finance. Although already very expensive in the region, borrowing is getting even more costly, and African countries with the highest needs for progress on access are particularly affected. And this alone could result in 2 million fewer people gaining access to finance by discouraging international investors. Also, the future is very concerning. A delayed recovery would see population without access to electricity increase to 630 million in 2030, a time when sub-Saharan Africa will concentrate 85% of global population without access. A similar pattern is also being observed for clean cooking, with population without access growing to 1.1 million by 2030, while in the immediate future, millions of households in rural and peri-urban areas are at risk of backsliding from modern fuels to charcoal, kerosene, or fuel wood. Now, let us do some interactive warm-up questions to test a bit your knowledge on energy statistics. So I would ask you to connect to the www.menti.com website. So you can use your phone or your computer to connect to this website, and then so this is the website. So once you're on the website, you have to use this code, which is 83, 81, 52, and 45. And you can answer the first question. So the first question is, what are the units used in an energy balance? So you have 4 possible answers. Do you think that we use physical units such as cubic meters or tons in an energy balance? Do you think that we use energy units such as megajoules, KTOE, British thermal units? Or do we use financial units such as dollars, euros, or you don't know? So please connect to the website and use this code to answer to this question. I give you some time. So the code is 83815245. So I see there's already one participant who has answered. Sorry, I think I just switched screen. So we already have a few people who are answering energy units. I give a bit more time as it is the first time that we use this tool. So I give a few more time for participants to connect to the website and use the code that appears on the screen to
Zakia, we still see the presentation, not the we're not seeing your Google page with
Really? Okay. Now?
no, we're still seeing your PowerPoint presentation.
Maybe I'll stop sharing and share again to. Now?
Yeah, this is now working.
Okay, sorry. So we have 17 people who have already answered. So indeed, this is the correct answer. In an energy balance, we use energy units, and it has many advantages of allowing us to put all the products next to each other and to compute the total energy produced and consumed in the country. So this is excellent. So let's move to the second question, which is, what is a calorific value? So here again, you have three choices, which is, do you think it's the quantity of energy contained in a unit of fuel? Do you think it's the temperature at which a gas changes of phase? Or do you think it's the monetary value or price of a fuel per unit of energy? So excellent. We have 21 people already replying. So again, very good. We see that most of you got the answer right. So the calorific value, it's indeed the quantity of energy contained in a unit of fuel. So one last question in this first session. So with which institutions do you cooperate for energy data work? So this is an open-ended question. You can write down the institutions with which you work. So tell us a bit about the different institutions that you work with. So GIZ, ZESCO Limited, Namibia Statistics Agency, Regulatory Board. AFREC, yes. IEA, very. So many of you work with the Energy Regulation Board, the Ministry of Energy, ZAMSTAT. Okay, I see answers keep arriving. SADC. Excellent. So thank you very much for participating in this interactive exercise. We will move back to the presentation now. And yeah. So yes, so can you see my the presentation now? Yeah. So this session, it will be divided into 3 parts. First, we will look at the fundamentals of energy statistics. It's very important that we start with discussing the basics, since energy data and statistics are the foundation that gives the ability to understand the entire energy systems. Then we will look at the implications of energy data collection at national level. We will break here for question and answers, and then we will go to the third part of the presentation, which is on the main energy data validation procedures and checks. So let's start with discussing the basics, since energy data and statistics are the foundation that gives the ability to understand the entire energy systems. As we all know, energy plays a key role in our economies, societies, and lives. Having reliable and high-quality data and statistics has always been a concern in the statistical community. Still, several decades ago, quality was not as good as today, and there were inconsistencies in the methodologies used. Many organizations were not using the exact same definition and scopes, so there was a need for harmonization for a common framework establishing standards. Today, the framework exists. It is the IRIS. It enables us to speak the same language. It is a comprehensive framework on the scope of energy statistics, classifications, units, methods, data collection, institutional arrangements, quality assurance, and dissemination. The IRIS has been approved by international organizations. In the early 2000s, the IEA undertook an initiative to organize a group, the Inter-ENERSTAT, composed of various regional and specialized agencies active in energy statistics. This group acts as the secretariat for the IRIS under the UNSD. It provides comparability of production, transformation, and demand flows over all products. The IRIS has been adopted by most international organizations, including in the African continent, the AFREC, and the West African Economic and Monetary Union. As having reliable and harmonized data is key for analysis and decision-making, we advise all countries to refer to the IRIS for their statistics. How do we structure energy data to get a picture of a given region or country? The key split is supply and demand. In the supply side, first you have the production in the country and from other sources. Then you add imports and you extract exports. You can consider international bunkers. There are several methodologies for this, and stock variations. As you can see, for stocks, you have arrows in both ways. Stock levels are very important indicator in data analysis. On the demand side, you have first the consumption by the energy sector itself and for transformation. For example, for refinery, you have the transformation that is converting crude oil into gasoline. You also have the industry own use processes like the steam crackers to create heat. Second, you have the consumption by end-use sector broken down by industry, transport, residential, commercial, agriculture, non-energy use, and many more. The two sides normally should match, but in reality they don't, and that's why we have statistical difference.
Statistical differences can show the data quality and therefore is a very useful indicator. So statistical differences can have a meaning by themselves. This breakdown by supply and demand work for several levels, at a country level, but also at aggregated regional levels. In which units shall we treat energy data? We need to agree on a common language. We all know many energy units. If in volumes, there are liters, cubic meters, barrels. In mass, there is grams, tons, pounds. And in energy units, you have the ton of oil equivalents, ton of coal equivalents, you have joules, watts. So we need to express information in energy units, and to do so, we have to convert from physical units to energy units using a conversion factor, which is the calorific value. The calorific values represent the heat obtained when the fuel is combusted. It is an indication of the quality of the fuel. The higher the calorific value, the higher the energy contained by unit of volume per weight. Therefore, it is useful to understand the quantity of energy. If you want to generate as much energy as possible, and I ask you to choose between 1 cubic meter of wood, 1 liter of oil, and 1 ton of coal, you need to know the calorific value to make the best selection. So calorific values have variations, and it varies among fuels and within the same product depending on the quality. See here the example of Morocco and South Africa, where you have the same product, which is bituminous coal, but with different calorific values depending on the quality. So whenever you collect energy data which is usually in physical units, you need to also collect the associated calorific value. It is even more complex as there are 2 different calorific values, which is the net calorific value and the gross calorific values. When you burn a fuel, you get the useful heat and water vapor that is not recoverable. Gross calorific values includes both, that is the energy of the fuel and the energy in water vapor coming from the humidity in the fuel when it is combusted. Whereas the net calorific values, it includes only the useful energy. Therefore, gross calorific values is always higher than the net calorific value. When a calorific value is reported, it is important to also ask whether this is on a net calorific value or gross calorific value basis. From one, you can calculate the other with standard ratios. Now, let us look at an example. When a country reports its energy data, it is usual to give one unique number for the physical quantity and one unique number for the calorific values. Here, let's take the example of a country with 2 fields of gas. Each field has a different calorific value and produces different quantities of gas. When you compute the total gas production, what calorific value will you use? In this case, we have to report the weighted average calorific value because it will take into account first the weight of each source of gas, and second, it will provide us a better estimate of energy supply and demand figures. Wrong net calorific values could bring to statistical differences, over-reporting or under-reporting in energy units. Now, we know that energy data will be reported in energy units. Let's see how to present all the energy data of a country. At the IEA, we use an energy balance. In the energy balance, all the flows and energies are represented in a single table, and everything is reported in a unique unit, which is the KTOE, kiloton of oil equivalent. You can choose another unit, but you just need to specify it. The energy balance is structured as such. First, in the rows, we have the flows, which is first on the top part, you have the supply. Then you have the demand, which includes the energy sector own use by a refinery. For example, you have the transformation, for example, from gas to electricity, from crude oil to oil products, and you have the end use consumption. In the columns, there are fuels and energies, and given that we are reporting everything in the same unit, you have on the right the total column. All this is very useful because all the energy data of a country are included in a table, and you can easily see the key information such as what is the first fuel in the energy mix in terms of supply, what is the first source of energy to generate electricity, which sector consumes the most energy. You can also compute sophisticated indicators such as energy self-sufficiency. Now that we are all clear on the basics, let us discuss more the process of collecting data in a given country. Here we present generalities. Everything might not apply to your country's context, but it comes from our experience of working with several countries. In view of the role and importance of energy statistics, one would expect basic energy information to be available in a reliable and timely way, but it is not that easy. If we want to have detailed and reliable energy data, it is helpful to have an entire ecosystem and set of enabling conditions. First, we need to have a collection system, and this includes several pillars. A legal basis with statistical laws and other national laws and regulations where reporting of energy data would be mandatory. The legal framework creates a necessary foundation, but it is not sufficient for energy statistics. We need to establish institutional arrangements to ensure collection and compilation of energy statistics in the most efficient way among all the relevant members of the energy statistics system. Another pillar of the system is a proper reporting and dissemination mechanism, which means questionnaires compatible with international standards, a network of contacts, and a data release calendar. It's better to work on data collection when you know for what publication you're getting the data and when it will be released. We also need to review the methodology, anticipate and adapt to changes and new challenges to meet national and international needs. For example, it is now more important to focus on new renewables and their full contribution to the energy system than in the past because of their particular challenges and their growth. Collecting any statistics has a cost. However, lack of data quality could lead to even higher costs, and there should be a balance between the efficient use of resources and collecting what is necessary. What is necessary will depend on the needs of data users. However, not all needs will be possible to meet. It is important to look at the changes in the energy sector and to limit the collection by cooperating between the relevant government agencies. Cost is one challenge, but there are others. There are challenges of specific trends or new type of energy activities. For example, biomass data collection is very challenging. Off-grid data is a new trend. The liberalization of the energy markets, which has two major impacts on statistics. First, while in the past we could obtain detailed information from a single national company, now many surveys are required to have a comprehensive view of a sector. Secondly, a competitive market often leads to confidentiality issues that add to the difficulty of collecting basic information. Other challenges are lack of resources and also the forced turnover of staffs. The process has several steps. We have to collect data, verify them, process data, and then disseminate them. Here we illustrate the data chain of energy statistics. Let's imagine a real activity. In a gas field, we extract gas, which is production. It is sent to the power plant, which is a transformation. And then we use the electricity for powering air conditioner equipments, drive an electric vehicle, and this is the end-use consumption of electricity. The data for all of these activities needs to be collected, and this step is called primary data collection. This is where you might be involved. That is, discussing with the utility that reports the quantity of gas used for power generation, conducting the surveys to households to understand how many air conditioners they have, looking for information on the consumption and efficiency of an air conditioner, etc. Then national administrations submit these data to international organizations in a certain standard format. For the IEA, it is mainly the energy balances. These data will be consolidated with others of other regions and compared to previous years. Once enhanced data are available, they can be used by first governments to shape energy policies, for example, to support electric two three-wheelers or energy efficiency standards for air conditioners. Then it can be used by the private sector and investors. And it can also be used by the civil society. NGOs can look at the CO2 emissions and call for more policies to reduce energy-related CO2 emissions. Who are the players involved? In terms of players involved in energy statistics, one of the most important one is the Energy Ministry, which sets policies of the country, and the other one is the Statistics Office, which is usually in charge of statistical compilation within the country. Usually some processes exist between the two for sharing data. The ecosystem is made of many other stakeholders, which are all very important, and collaboration between them is key. Energy regulators might have a lot of data, but they would have an incomplete view of the supply side without trade data. This is true for imports of fuels, but can also be interesting for off-grid solar systems or solar panels. Information on the demand side will also be incomplete without some form of comprehensive surveys. Ministry of Transport may have data on cars and trucks that will complete your understanding of energy statistics. The Statistical Office and Energy Ministry can then hold large amounts of data, but further collaboration is needed to make sure that appropriate outputs are disseminated and used accordingly, and that the right institutions are involved at each stage. What tools can be used for getting data? There are several possible sources, such as administrative sources. You need to check first before starting, because maybe some data are already available. The second one are surveys. It's quite challenging and we need to be careful when we do sampling. The advantage of surveys is that if you have existing surveys, you can just add a question. Example, asking a question on source of lighting, fuel for cooking during a demographic and health survey. Metering. Metering is very relevant for energy infrastructures, energy transformation, and for industrial consumers, but it is costly. Another tool is modeling. We do not mean to make projections and forecasts. What we mean is that we can estimate historical data based on proxies. For example, in 2018, you have a survey that gives energy consumption of household. You can define a proxy based on incomes and calculate for previous years if you know how this proxy has evolved. One important point is statistical confidentiality. Confidentiality should be taken very seriously. It is necessary to prevent unlawful disclosure of confidential data. But in some cases, confidentiality can be used as an excuse for not disseminating data. Solutions can be found in order to have more published data. And so a dialogue between the government and the private sector is needed in order to ensure that the data becomes accessible and treated without negative consequences for the company providing them.
So now we will pause here to see if we have some questions and answers, and I'm joined here by my colleague Julia, who is an expert on energy data, and we are happy to take over your questions. I see that in the Q&A, there is a question on what does BCM stand for. So BCM, it's billion cubic meters. There's another question, which is from Sikawala. I hope we will get the presentations. We are working on collecting data in energy. Yes, so all the presentations, normally they have already been shared on Google Drive, but we can share them again with you if you have not received them. And also all the material will be put on YouTube. So even if you miss part of it, you will be able to view them whenever you want. You can watch the video. Do you have more questions?
Sakia, there is a question asking to go back to the formula for average calorific values.
Yes, I'll try to put the present. I don't remember where exactly it was.
Maybe in the meantime, I can try to answer.
Yeah.
So the idea of computing the average calorific value is that when you have different places where you get your fuel, for example, the coal or gas, it will be produced at different places. And so in order to make national energy statistics, you will have to compute the average that will be usable. And this is going to be weighted in function of the quantities that you receive in the different fields. Yeah, and there is the formula. So that is why here you basically take the gross calorific value of field number 1, field A, you multiply it with the production, the quantity of field A, you add the field B, same gross calorific value of field B times production of field B, and you divide it in order to weigh it by the total weight, the total volume in this case, actually, production A plus production B. I hope that's more clear. So of course, if there were 3 fields, we would do the same. We would add on the nominator, we would add GCVC times production C, and on the denominator, we would add the production of field C.
Thanks, Julia. We have another question on, is data verification and validation different in energy modeling? I only saw the verification process. So the third part of this session now, we will look at data validation. And in modeling, it is not so different as well, except we take also into account the different assumptions for each scenario that we are looking at. So TG, it's terajoule. We had another question. So if we don't have more questions, we'll move on with the presentation. So I go back to the presentation now. So yes, so before we start the third part of the presentation, let's do again a few Menti questions. So can you please connect again to www.menti.com. And I will also connect myself. Trying to find it. Mm-hmm. Do you see my Menti? I'm not sure it's, yeah.
No, we don't see it.
Yeah, now.
Yeah, now it's.
Yeah, so again, you can use the same, it's the same code as before. So 83, 81, 52, and 45. And the question is, what are the types of checks you can apply to energy data to ensure quality? So this is an open-ended question. So we would like to know of the different types of checks that you're aware of when checking data. Give you some time to type your answers. Yes, calorific values. It's good to check. As we said, it's a good check. The units. Statistical difference, yes, this is a very good one. Yeah, percentage, I think growth rates. Generation data. Yes, you can compare your generation data, so your output with your inputs. The source, yeah, you can compare different sources as well to see if it makes sense, the data. Outliers, yes, if you see a big increase or a big decline, there needs to be a reason behind. Sources input, yeah, especially for electricity or for other different transformation. Meter readings, yes. Very good. So I see we have a variety of checks that you are aware of. So let's move to the second question. So how can you verify the fuel consumed, that is the input, and the electricity produced, which is the output, by a thermal power plant? So how can you check your input and output? Is it by analyzing the trend of production in the past years, depending on technology? Is it by comparing the ratio output-input with expected efficiencies? Or is it by comparing the level of production with similar countries? So we have 15 participants who say it's by comparing the ratio of output-input with expected efficiencies by technology sources. Analyzing the trend of production in the past years, we have 4 participants who say that's the way to verify. Here, again, most of you got the answer right. So the way to verify that your input and output makes sense, it's by comparing the ratio of output and over input with expected efficiencies by technology. One last question is, what do you think is the efficiency of a traditional earth kiln to produce charcoal? So is it around 80%, is it around 40%, or is it around 20%? So what is the efficiency of a traditional earth kiln to produce charcoal? Give you some more time to answer this one. So here the answer is indeed around 20%. So a very traditional earth kiln, it's the efficiency is around 20%, but you have some improved traditional earth kiln that can go up to 40% as well. So the answer is around 20. So most of you got it right. So now we'll move back to the presentation, and we will go and see about the data validation.
Let's start with a summary of the recommendations to establish an energy information system. One should establish a solid legal foundation. Also, it is important to ensure institutional arrangements, to build up formal procedures to support confidentiality, and to establish a data collection strategy. One should also provide up-to-date metadata and follow the international standards and concepts. Let's now have a look in more details at the data collection strategy. First, to establish an energy data collection strategy, one should identify data needs, both on the national, on the regional, and on the international scale. Then, one should look at the data that is already collected by NSOs, by other ministries, by other public actors, private actors, and by international agencies. Once these are compared, we will be able to identify data gaps, which are the data needs that are not yet collected with the proper requirement levels. That could be on frequency, on level of detail, on definition, etc. Then it is possible to establish a strategy to collect the required data and include it in the national data strategy. This should include a legal framework, the allocation of resources, and the procedures for data collection and validation. And this is what we will have a look at now, the data validation. Data validation is important to ensure good data quality. And data quality is defined with 5 main aspects. First, relevance. The statistics should meet the needs of the users. Then they should be accurately and reliably portraying reality. They should be released in a timely and punctual manner and be consistent internally over time and comparable between regions and countries. And last but not least, they should be presented in a clear and understandable form, released in a suitable and convenient manner, and available and accessible on an impartial basis with supporting metadata and guidance. And for more information, you can see the links below. How to ensure data quality? We need to do different data validation steps. And the first thing to do is to check the internal consistency. Things to look out for are if one field is supposed to be the sum of 2 others, is it? Does the detailed breakdown match the total? Are stock changes correctly calculated? Is the data set complete? Is the decrease in use of one fuel coupled with an increase in use of another one? Or can you explain it with other reasons like efficiency improvements? And is the story logical? Then it is also good practice to analyze the data validation processes to identify possible points of failure and introduce checks. An example with this process A. Process A requires extracting fields, summarizing data, and reformatting data sets. It is easily happening that 1 or 2 items are dropped from the large data set. Because of this, one should compare before and after counts and the totals of data. One other aspect are the statistical differences. Indeed, when we collect energy data, we try to get a picture of supply and demand in a market. And in economic theory, we would expect that with an equilibrium, supply is equal to demand. The supply is how much is available to the internal market. The demand is how much was consumed in this market. In practice, as measuring supply and demand comes with challenges, and often we have different sources for the both sides, there can be a difference, which is the statistical difference, the difference between supply and demand. And this statistical difference can help us validate the data. Indeed, high statistical differences can be a red flag, often when it's more than 5% of the deliveries to the market. But we say that a statistical difference of 0 can also be suspicious, as it might mean that it was hidden in one of the commodity balances flows. So what can I do if an issue arises with a statistical difference? One should check the completeness and coverage of the data, check if there is double counting. One could have a review of the definitions and methods of data sources, check calorific values for supply and demand, and check if there are any new trends missing in the dataset. A specific example to verify electricity statistics is to verify the on-use and the transmission and distribution losses. First of all, the on-use. On-use of electricity by power plants as a proportion of production is not expected to vary significantly year on year. So this is something, when we map it over the time series, that we can use to validate the data. Similarly, transmission and distribution losses should not go above 10%, at least the technical transmission and distribution losses. However, it can happen that with bad maintenance of the grid or theft, we have higher transmission and distribution losses. We can see it in the graph on the right side. Several regions around the world are higher than 10%. It is just important to be able to explain these differences and potential changes from one year to the other. Calorific values are not only important to the energy balance construction, but they also allow us to check and validate the data. Indeed, for every energy product, there is an expected range for the calorific values. And that's why we will be able to compare the collected calorific values against default calorific values. We can also compare them with historical calorific values for the product, because they can be region specific. And last but not least, one should check if the NCVs and GCVs used for consumption are in line with the ones used for supply, because this might lead to statistical differences. Another element that can help for data validation is the growth rate. This involves comparing the data point of the latest period to that of the preceding periods. And this is the formula. And if there is a high growth rate, one should be able to explain it by real-life facts. When seasonality is strong, or we are dealing with monthly data, it is often more useful to compare the current months with the same months of the previous year. And in general, this strategy is very useful for production and consumption, but less useful for stocks and trade. Breaks in time series can happen. You can see two examples on the right side in the graphs. However, we want to aim for a consistent time series. And if there is a break in time series, we want to be explaining it and to avoid unexplained breaks in the time series. Breaks in stocks are rare and should be investigated. And in general, certain flows are consistent over time, where then a sudden increase or decrease will raise a red flag. One example is the refinery intake graph on the right side on the bottom. Here you see that for 1 month, April 2005, we have a very small refinery intake. And for 1 month in December 2005, we have a very high refinery intake. While the first break in time series can be explained by maintenance, for example, the other one is more difficult to explain. And this is something that one should check, because usually refinery intakes stay quite constant at constant levels over time. Now let's have a look at transformation efficiencies. These can also help validate the data by looking at the relations between the input and the output. Indeed, for every energy transformation process, there is an input and an output, and there is a relationship between these two that will depend on the technology used. The efficiency will be calculated by the total useful output in net energy units divided by the total input in net energy units. For an example here, you have two inputs A and B and one output C. The efficiency will be calculated as C over A plus B, whereby the inputs and outputs need to be both in the same energy unit and in the same energy form. This efficiency then needs to be checked against the expected ranges for that process and technology. An efficiency larger than 100% is implausible, so that would be a first red flag. And then we will expect efficiencies to be within a certain range depending on the type of plant and the fuel used. They can also vary widely depending on the state of technology. a very old power plant will be less efficient than a very new one. And in general, efficiencies do not vary significantly from year to year as technology upgrades are time and capital intensive. Here is an example of the expected efficiency range, but this is very much country and technology dependent. So don't worry if you have an efficiency outside the range. It's just good to double check and to see if you can explain this difference. Another element to verify the data is to check if the data set is coherent. Are we able to explain trends in data sets? To do that, we can verify the data is coherent with certain related trends. For an example, we have here in sub-Saharan Africa, the increase to access to electricity. And this is also visible in the increasing electricity generation. So here the two data sets are coherent. Then certain patterns may also be fuel specific. For example, natural gas demand and storage is linked to weather patterns. Hydroelectricity production is affected by rainfall, etc. Then one should also check if the data match related data collected through different sources. For example, the input to electricity production from electric utilities should match the fuel used in power by other sources. And in most cases, there are relationships among variables, such as the efficiency that we have talked about, that have to be satisfied. For example, if the inputs to power production are increasing, we expect that the outputs will increase as well. And a decrease in input without fall in output can be the result of improved efficiency. And this is the case on the right side for the gas power plants in sub-Saharan Africa. We had in 2000 an efficiency of 30%, and at the end of the time series in 2017, we have 40%. So this explains the difference between the evolution of the input and the output, the electricity production. Another data verification is to check the coherence with economic data. GDP and population data can serve as indicators of data consistency. One can check if the GDP or population is growing steadily, and if the energy consumption data makes sense in light of this. Long-term demand trends can also decouple from population or GDP because of efficiency or increased access. But here again, it is important to verify that the story is logical and that you are able to explain trends with real-time events. An example is here the total primary energy supply in the IEA. We see a dip in 2008-2009 in this total primary energy supply. And when we look at the gross domestic product in the IEA countries, we see the same dip. This is actually because there was an economic crisis. And so we are able to correlate one data set with the other one and to explain through economic data. Then it is important to have a look at different data sets and reconcile them when there is a different product classification. Because in general, goods can be classified using three systems: the harmonized system, HS, the standard international energy product classification, and the central product classification. And differences in product classification can quickly lead to discrepancies in data. For example, sometimes fuels with similar qualities can be named differently onshore and offshore, and categories do not always match. For example, biodiesel in the harmonized system can include up to 70% of oil from fossil origin. So this is important to note. And if you have two data sets and have difficulties reconciling them, think about the fact that there might be a difference in product classification. Then you can also try and reconcile different data sources by mirroring checks. This is particularly useful for data sets with a bilateral component, for example, for trade. This helps ensure the consistent interpretation and application of methodology and avoids double counting or missing flows. The goal should be to limit, justify, and explain discrepancies when existing, and it's important to work with partner countries to investigate. The IEA can help you with this. An example on the right side in the graph with electricity trade. Here we see the electricity trade reported on the one side from country A, by country A, from country A to B, and on the other side in red, as reported by country B. We see that they were quite consistent along the time, and then around 2013, something happened, and there was a big discrepancy between what both reported. So this is something where we would go back to the country and ask. Discrepancies can arise when we deal with trade data because of different methodologies. For example, physical flows versus contractual flows, or the country of origin destination might be changing. Then there can also be a problem with timing, and different countries may have different definitions. That's why detailed and transparent metadata is essential. Then we can also verify coherence when using monthly and quarterly data as an extra to the annual data. Indeed, good quality monthly data can be a tool for data validation, as well as is key for energy security purposes. We see here on the example for LPG across the years that the monthly data had always been quite consistent with the annual data, except in 2016. So something to look out for are revisions and different definitions or coverage due to timing constraints. Again, in the example, the monthly data was always a little bit lower than the annual data, which points to different coverage, maybe timing constraints, because it's easier to have all the data for the annual, which is later on, than for the monthly. However, in 2016, something happened because we have a much bigger discrepancy. So that would be something to query. Last but not least, if countries are not in a position to meet the accuracy and timeliness requirements, they can produce provisional estimates. However, note that these are based on less comprehensive data content. So what to consider? It is preferable, of course, that almost all data are real observed data. Estimates should only be used for flows and products that represent a small proportion of the balance. And they should only be used for a short time whilst a system of data collection is being established. Strategies will depend on whether the data needs to be systematically estimated or if it's only missing exceptionally and you know that it will be provided later on. Whenever a data point is estimated, this should be clearly marked and defined in the metadata. In general, we will ask the following questions when we estimate data. Is someone else already collecting this data or related data? This would avoid the time needed for the estimation. How important is the flow or product? This will tell you how much resources one can put into the estimation. Is it correlated with another flow for which there is data, which could help you to derive the data from that flow? Is there a seasonal or historical trend that can be used for the estimation? Why may this period be different? For example, have a look at the heating degree days for space heating. Can market trends be used as an indication or input for estimation? Last but not least, we will describe how the data validation processes are done at the IEA. An overview of how the data is processed and validated at the IEA is first, we will receive the data. Then we will process it, look at the inconsistencies such as the breaks in stocks, negative values, errors in sum, etc. Then we will do some time series checks, consistency, balance checks, seasonality and outliers, calorific values, and iterate with our data providers on these two types of checks. If we receive new data, we reprocess and we recheck the time series. Then we will have some more checking and peer review where outliers and seasonality will be checked again, and then the database is frozen. And finally, we will disseminate our data. If you want to learn more about energy statistics, we have produced a comprehensive energy statistics manual that covers most of our data collection methodologies, and it is consistent with the IRIS framework. It is available in 10 languages, and you can download it free of charge. Furthermore, we have talked about it already, the international recommendations for energy statistics are available on the United Nations website. And we have also some manuals for indicators and policymaking that are available on our website. The IEA data products include data services for purchase, but also free products on our website, including the keyword energy statistics, a data browser for data and statistics, the energy balance flows in form of Sankey diagrams, etc., etc. I invite you to have a look at our website. Thank you very much.
Thanks. I'm going to go back to the presentation now. It's time for question and answers. If you have questions. Let me see. We have a few questions in the Q&A box. Kindly elaborate what you mean by stock changes.
Yes, so stock changes are the variation in stocks in the reporting period. So in the case, for example, that we are looking at a year, we will look at the difference in stocks between the beginning and the end of the year. The convention is that at the IEA, at least, we use the convention that we will take initial minus final stocks. So that will be our stock changes, which means that if we have negative stock changes, we have bigger stock level at the end of the year. But this can vary from statistical office to statistical office. Then I think there is a question on the data providers for Zambia.
Yeah.
So I think this is data providers to the IEA. So it's the Zambia Energy Regulatory Board with the statistical bulletin.
Yeah, and tomorrow we will have Nicola Cohen, who processes the Zambia data, so we can answer this in more details. And there's a question on metadata.
Yes, so metadata is all the information that is basically not data, but that will allow the user to understand what is behind it. So all the information on the sources, on the assumptions that you might have taken. At the IEA, for example, with our database, we also release a PDF documentation, which explains the definitions of the different products, the definitions of the different flows, but also the sources for every country and the different assumptions that were taken.
We have another one about unexplained breaks. This is not a question, but a comment. Indeed, unexplained breaks should be investigated. Sometimes it can't be avoided because if you have a recession or, I don't know, a power plant that closed down, so then indeed you have a break in your time series, but indeed there need to be good reasons for the breaks. I don't see any more questions in the question and answers. We still have a few more minutes, so do not hesitate if you have questions. to ask us. Well, then if we don't have any more questions, we will close down for today. Thanks, Julia, for joining for the question and answers. And thanks to all the participants who have participated actively during the session. We have another question now. How do we account for stock? Julia, do you want to take this question?
Okay, so the question is, how do we count for stocks in the energy balance? So this is basically what we were discussing before. We will represent the stock changes in the energy balance, because that's what we are interested in. We are interested in the products that are used in the reporting period, let's say in the year, domestically. So basically, if there is quantities taken out of the stock, this will be visible in the stock changes, since they are calculated as initial minus final stocks. And so these will be reflected in the line stock changes in the energy balance.
Yeah.
I hope this answers the question. Of course, don't hesitate to.
And then depending if it's a stock build or stock draw, it has a positive or a negative sign. Yeah. If I don't see any more questions. No questions. Then I think we are done for today. So tomorrow we will go deeper into the fuels, into the different fuels of the energy statistics, and we will also look at an exercise in the end of the webinar. I think you have all received the exercises in advance. If you have not received it, please let us know and we'll send it to you. And we recommend that you try to do it by yourself in advance, so that during the session tomorrow, we will just do the correction and answer your questions for the elements that you have not understood or you want us to elaborate more. So thank you very much, everyone, and see you tomorrow at the same time, so at 9 a.m. Bye.
Thank you. Goodbye.
Bye.